Welcome to this class on neuroscience of human movement. We have been talking about skeletal muscles. Today's class will be part 4 of our discussion on skeletal muscles. So, in this class we will be talking about muscle torque and joint range of motion and how muscle torque and inertia are related. The situation is, how are even human movements produced? What is considered movement? What is presented here is a simplified version of the actual situation. Obviously, the actual situation is way more complicated, and we have taken a very simple version to understand the concept, to understand the principle. Okay. Let us consider a case where there is a flexion action being performed, right. So, that may be similar to that action. Okay. For the purpose of this course and class, we will define flexion or a movement that reduces the angle between two segments, okay. Two neighboring segments. If the angle between them is reduced, we will call that as flexion. Actually, there are several definitions. I am not going into the details, but for now, suppose I have the elbow joint, right. That is the elbow, and as of now this is approximately at right angle, approximately this is at 90 degrees. I am doing that. Now, that angle is slowly reducing, right, slowly reducing. That is called flexion. That movement which reduces this angle is called flexion. When I do the opposite, it is called extension. Okay. You note I can extend at up to 180 degrees, that is approximately 180 degrees, whereas I cannot flex to 0 degrees actually, because there is tissues that prevent these two bones to actually become parallel to each other. So, that is not possible, right. So, it cannot be 0, but it is a small value, there is a minimum, say 20 degrees or whatever. So, the angle between these two joints may be 20-30 degrees at this level, and it is 180 degrees. This is called range of motion, right. How is this movement happening? Actually, this particular movement is happening through the interaction of multiple muscles, but we will consider a simple case. Okay. Let us suppose this is the joint around which the movement is happening. Okay. This is the joint J about which the movement is happening, right. Now, if I have to reduce this phi is the joint angle which is approximately 90 degrees in this case, I would like to flex or reduce phi. In that case, what should happen? Let us consider that this joint is spanned only by two muscles. For the purpose of discussion, there are only two muscles. One muscle is this, which I am going to call as flexor, and the force produced by this flexor is F flex. The other muscle is this, which is called as extensor, and the force produced by that muscle is F ext. If the flexor contracts, then what it will do is essentially this will reduce or that will happen, is it not? Something like this situation will happen. So, earlier this was the configuration, earlier the joint was at approximately 90 degrees. Right. Suppose when the flexor muscle is contracting, then what happens is this, right. Say for example, at the end I am supporting a load here, some load, that value I am going to call as F load. Let us assume that there are no other joints that are being spanned. I am simplifying the situation so we can understand the principle. So, suppose there is no other joint involved here, that perpendicular distance between the load and the joint is some distance d segment. Now, I would like to hold the object in equilibrium. Let us assume that this object is about 10 kilograms, right, and I have to hold it in equilibrium. If I have to hold it in equilibrium, I have to produce an active force with the flexor muscle, because otherwise if I did not produce, this will drop. But I want to keep it in equilibrium, I want to keep it in that configuration, I want to keep it in equilibrium in that configuration. By the way, it is also possible for me to keep it in equilibrium at multiple configurations, for example that configuration, for example that configuration, or for example that configuration. I can do that in multiple configurations, but for now I am interested in this configuration where there is a right angle between the upper arm and the forearm, right. So, in that case I have to produce an active force with the flexor muscle such that the moment or the torque that is produced by the load is overcome by the torque that is produced by the muscle. Let us analyze that situation a bit more deeply. So, the torque that is produced by the load is essentially the product of the load itself times the perpendicular distance between the load and the joint about which, or the axis about which the movement is happening. The joint about which the movement is happening is here, the load is here. In the case of the forearm that we just now discussed, this d seg is about 25 or even 30 centimeters. So, if I had a 10 kg mass, then I am talking about the load being 10 into 9.81 or essentially 98.1 newtons times 30 centimeter. That is the approximately 294 Newton centimeter. Note the unit, it is not Newton meter, Newton centimeter in this case, right. Now, that is the load that is that is the torque that is being produced by the load on this system. Whereas, note the muscle is attaching at that point, it is not this distance that we care about. Let me erase this, so things are a bit clearer, right. This is where the muscle is attaching, but it is not this distance that we care about for the purpose of computing the torque, it is that distance. What is the difference? Essentially the torque is the product of the force and the momentum. What is the momentum? The momentum is the perpendicular distance, the shortest perpendicular distance between the line of action of force and axis of rotation. So, essentially this means that is what we care about. In this case, it is immediately obvious that d segment is actually a constant at that angle. Actually, at a different angle again, since the load, something to remember is, since the load always acts downwards, and in this case it is convenient that d segment actually is the length of the forearm, but that is only in this case. At different configurations, d segment or the momentum of the segment will vary depending on what the joint angle is. Here I have chosen a convenient coordinate system such that d segment is the length of the forearm, but this may vary in other configurations as we will see in future slides. So, but at least one thing is clear, that this is d flex, and this d flex is also a function of the angle phi. At different angles you will have different momentums. Now, that means it is not clear for me what is the force that I need to produce. Then how does the system learn this? That is one question that we will have to address in future classes, but for now we will assume that there is this d flex or the momentum, and there is this d seg or the momentum of the load. D flex is the momentum of the flexor, and the muscle force that is produced by the flexor is F flex, and the torque that is the force that is produced by the load is basically F load. Then essentially you are looking at equations of static equilibrium, which is basically sigma Fx equal to 0, sigma Fy equal to 0, sigma m is 0. In this case, if you choose convenient coordinate systems, sigma m alone if you write, you will essentially get for the purpose of this course I will use, instead of m I will use tau for the moment of the torque, because m's can sometimes be confused for muscle force. So, I will use a different notation. So, this is essentially F flux times d flux, which is counterclockwise moments. So, sigma tau, where counterclockwise moment is considered positive. So, that is essentially a counterclockwise moment, minus F load times d segment, and that is 0. Important to note here is d flux is usually a fraction of d segment. D segment is of the order of 25 to 30 centimeters, whereas d flux is usually a few centimeters. For convenience I am going to say that is about 3 centimeters, whereas d segment is about 30 centimeters. Now, it makes my problem easier to solve, and let us assume that the load that I am carrying is instead of 10 kg I am going to call that as 100 newtons. To simplify my problem, I am going to assume following values for the forces and momentums. These are, I will write here, F load is 100 newtons, okay. D seg is 30 centimeters, d flex is 3 centimeters. The question is, what is the muscle force that is produced? That is the question. Using that equation, I could compute F flex as F load times the d seg divided by d flex, and that is basically 100 times 30 divided by 3, which will essentially give me 1000 newtons. Now, essentially realize that is a relatively large number. 1000 newtons is what needs to be produced to carry a 100 Newton load. Why is this? Well, obviously this is because this distance or the point at which the muscle attaches or the insertion is closer to the axis of rotation or to the joint when compared with the load in this case, and this is usually the case in many such systems. So, usually the muscle force that needs to be produced is many times the actual load, right. So, that is because of small momentums. In this case the situation is that there is a small momentum, or sometimes it turns out that they attach at inconvenient angles such that the rotation is not happening about the joint under consideration, but actually happening about multiple joints, one of which is this joint. In that case, what happens is you have to make the movement about this joint and prevent movements about other joints. Those are other problems that come with the situation, but for now it is enough for us to realize that that the muscle force can be many times the load. In this case, that is because of small momentum. In other cases, it may be due to inconvenient angles of attachment. All right. Now, what would happen if I were to do this at that level? Well, the problem slightly changes, right. Now, let us remember, since the load is always acting in that direction, right. If I choose that as the xy axis as the frame of reference, I will have a theta, right. This theta is actually small, right. For small theta, sin theta is theta and cos theta is 1. Again for relatively small theta, that is the actual momentum and that is the length of the forearm. So, here there is a slight change in the problem. Why? Because now you have an acute angle, right. Earlier I had a right angle, now I have an acute angle. Accordingly, the problem will change. Of course, it is possible for me to choose a different coordinate system. Whichever coordinate system that you choose, depending on that, the problem will change, but it is not like the force that needs to be produced by the muscle has changed by a lot. Regardless of the situation, D segment deflex is not going to vary by a lot. And by the way, deflex, which is the momentum of the muscle, actually varies as a function of the phi. Deflex is a function of phi, and it reaches a maximum around the joint's middle of the range of motion. So, if the joint has a range of motion of say 100 degrees, then at about 50 degrees you are going to have the maximum momentum. Okay. So, then the torque that is going to be produced is actually the product of this momentum and the force. So, you are going to produce the maximal force at around the same point. It turns out that the maximal force is also produced at around the same point in many cases, but there are exceptions. So, the maximal torque is produced at around the center or the middle of the joint's range of motion because of two reasons. One is the maximal force is produced at that region, and the momentum is also maximal at around the same region. So, which is why you are going to have a maximum tau at around that region. The relationship between deflex and dseg are not going to change greatly depending on whether the angle that is being considered is a right angle or an acute angle or an obtuse angle, because this is a relatively small distance. The point at which the muscle attaches to the distal bone is called as the insertion. This is something that is not going to change. What is going to change is phi and essentially the momentum, but this point itself, that point does not change, right. And essentially the relationship between deflex and dseg will remain such that the muscle force is usually a very large number when compared with the load. This is the usual case. Now, what happens if I have to produce an obtuse angle, right, like that? Now, again the situation is the same. The situation is I am once again having a dseg. Now you know, if I use that coordinate system, you know, so now that is the momentum, is it not? That is the momentum, and this is dseg, and this is going to be a relatively small theta in comparison with phi or in comparison with so in once again deflex is going to be small in comparison with now that is dseg. This is essentially forearm length or length of forearm, something of that. But the situation is actually somewhat complicated, more complicated than this. So far I have only been discussing the case where there is only a single muscle. Actually what happens is there are two muscles that span, at least two muscles that span this joint. Now that is the joint under consideration. If I want to flex, if I want to reduce the angle, right, if I want to do something like that from the neutral position, if I want to make the angle an acute angle, right, if I want to do that, that is basically flexing. If I want to flex, that action is done by that muscle. If I want to extend, that action is done by that muscle or that force. Now that seems like a inefficient arrangement. I am having two torque motors to produce movements in two directions. A smart engineer would do the opposite, they will have only one motor and essentially change the current, so that the motor rotates in opposite direction. So, there will only be one motor, but here there are two motors. Actually the situation is, physiological situation is way more complicated than this. Actually there will be multiple muscles that span the same joint, okay. That is not been discussed here. Why does nature prefer this arrangement? That is one question, we will have to discuss that, right. So, I have two muscles, one producing flexion and another producing extension in this simple case, right. One is making that movement, the other is making that movement, right. And the net torque is basically the torque that is produced, is basically the vector sum of all the torques that are involved, right. Essentially, if there is no load, or if you assume that the forearm is massless for the sake of discussion, if there is no load, then what happens is that the net torque is basically the vector sum of these two torques, right, or the flexor torque and the extensor torque, that is what is being written here. Now, once again the net torque is basically the vector sum. In the case where there is no load or the forearm is considered massless, we will have to change the equation depending on the situation, right. That is the situation with the joint torque case. Now, let us say that I am actually interested in producing a trajectory. X axis here is say time, and the y axis in this case is you know theta. Now, that theta, let us say I am producing a relatively smooth slow movement, I am producing something like that. If it is a slow movement, you are going to have activation, if it is increasing theta is considered extension, say for example, right. So, that is increasing theta. In that case, then only the extensor will be active if it is slow movement, okay. What will the velocity look like? The angular velocity will actually look, okay, the angular velocity will look like that, approximately there, or somewhere earlier you are going to have the peak. So, that is theta dot times t. How will the acceleration look like? That is how the acceleration is going to look like. So, essentially you want to reduce the velocity. If you want to have minimal variability at the end point, actually that is something that we desire. We would like to reach the end point as planned with very little variability or a small amount of variability. Then I am interested in controlling my movement in such a way that I stop where I want, otherwise I will overshoot, right. By the way, those are diseases, dysmetria, overshooting, undershooting, these are diseases, right. Reaching the target approximately accurately, almost accurately, is a sign of health, right. So, that is possible if I start slowing down as I am getting closer to the target. So, essentially that is what this means. So, the velocity peaks to a point and after that it reduces, right, and it is almost 0 when you have reached the target, right. So, this means you will have that sort of an acceleration curve. This is for slow smooth movements which are usually produced by the action of a single muscle, right, the extensor muscle. If you want to produce a quick movement, right, I am having the flexion like that, right, like that, an accurate movement like that. If I want to produce quick movement, then I am interested in braking braking as in like in driving you want to brake, you want to apply the brakes. If you want to slow down, you can reduce acceleration, or you can reduce the velocity, right, of one motor of the engine in the case of driving, for example. The better way, if you are driving too fast, right, the better way and the must thing to do is to have good brakes. I want to brake, I should stop accelerating, of course I should stop accelerating, but I should also brake if I want to come to a relatively abrupt stop, right. Now that is achieved in this case by the combined action of two muscles. In that case what happens is, at around that area, at around that time when the velocity peak is reached or sometime before or after, the antagonist, which in this case is the flexor muscle, starts getting activated, that starts applying a brake. So, there is co-activation of the antagonist for a brief amount of time during the movement, that essentially reduces the effect that the agonist has. In this case the agonist is the extensor, the antagonist is the flexor. For what action? The action is extension, right. For extension the agonist is the extensor, right, when I am doing that. Now, if I want to come to an abrupt stop, then I must apply brakes or activate the flexor at an appropriate time. Now, essentially this means that there is a synergy, a coordination between muscles. Actually we have discussed only the simple case of two muscles. Actually both the extension and flexion can be produced by multiple muscles. That means that there are many ways in which you could overcome the forces or the loads, but that also means that you will have to control this availability of other options much better. So, there is the luxury that you have with the system having many degrees of freedom, but there is also the problem that you will have to control many more degrees of freedom. So, that is one. The other case is preventing unwanted movement. Now, how is that achieved? There are several things. Why do we care about this? It turns out that many muscles have more than one action. They are not pure flexors or pure extensors. They also cause rotation about other joints. This is because of attachment at the insertion at inconvenient angles, at other angles that you do not want. Since essentially the muscle force is produced along its tendon, it is going to cause rotation about multiple axes, some of which may not be wanted. Quick example is the case of supination, right. Now, when my arm is pronated like that, so this is called pronation, this is called supination, right. How do you know that this is supination? How do you remember that this is supination? Well, supination is when you can hold soup, right. Now, here I can hold soup, this is called supination, this is the other one is pronation. So, this is pronation. If you would like to supinate, right, there are two muscles that are responsible for this, one is called as a supinator muscle, the other is called biceps. But biceps is also responsible for flexion. Now, the question is depending on whether you want to produce flexion or supination, you activate biceps and you activate the antagonist of the other action. What this means is the following. What this means is if I would like to say supinate but not flex, if I would like to supinate but not flex, I would like to supinate at that angle. So, my hand is pronated, I would like to supinate without flexing. In that case, I will use biceps to supinate, right, I will do that, but when biceps is active, it will also cause a flexion action, it will also produce a force in the direction of flexion, but there is no flexion, I am supinating without flexion, right. How is that happening? Because the antagonist of the flexion action, what is the antagonist of the flexion action? In this case, that is the triceps. The triceps is activated simultaneously when I am going to supinate at a relatively equivalent level of activity or equivalent level of force that will overcome the flexion force. So, biceps actually produces a flexion force and that force is overcome by the triceps force. So, that flexion does not happen, but supination does happen. This is a relatively common phenomenon, this happens all the time. The question is that means we will have to activate several muscles for producing one movement. The answer is yes. So, that means that is also energetically expensive. Also, the other reason why you want to avoid unwanted movements is when I am moving say the proximal part of the body. So, usually the part of the body that is close to the center of the body is called proximal, those that are away from the center of the body are called distal, right. So, that means the fingers and the hand are distal parts of the body, whereas the upper arm and the forearm are relatively proximal, right. Now, if I am making a relatively fast movement of the elbow, my wrist position remains approximately the same like that, relative to the forearm wrist position remains approximately the same when I produce fast movement of the elbow joint. How is this happening? Usually what will happen if there is no activity at the wrist joint, what will happen is the following, let me try to do that, right. See what happens is there will be flailing of the distal joints, there will be flailing of the distal joints when the proximal joints make movements if there is no compensation, active compensation that is happening at the distal joints. Why? Because these are distal to this, they are attached to this segment, right. When there is movement in this joint, in the proximal joint, that movement is going to produce a force, produce some action on the distal joint which must be actively overcome by the distal segments. If that is not happening, they will be flailing, right, which is undesirable. To avoid this flailing, what is usually done is there is co-activation of wrist flexors and extensors and abductors and adductors depending on the actual action, intended action. Depending on that, there will be simultaneous activation of muscles in two different directions, thus increasing the apparent stiffness of the joint. Then this joint becomes stiff, it is like I have locked this joint in place. Now then when I make the fast movement, this joint is already locked in place, but there is no physical lock, essentially I am supplying energy to lock this in place. Now that means I have to spend energy for overcoming unwanted movements in this case. This is again a very common phenomenon. The same similar thing can be said about how if I would like to flex the wrist without abducting it. So, usually wrist flexion is made possible by the radial flexor, right, but this also causes an abduction. Let us say that I am not interested in abducting the wrist, I am only interested in flexing it, then I will have to activate another muscle that is producing the adduction action, thus producing only the flexion. The advantage of having multiple muscles spanning a joint is that the same movement can be produced by different muscles. The disadvantage is that you need to have very good control, right. There must be good neural control, timed control of this. Also the advantage of having one muscle having multiple actions is that you do not have to have too many muscles. The disadvantage is that every time you want to produce one action, but not the other, you should also activate the antagonist of the other action, right. So, this is a problem. So, essentially this results in coordination between multiple muscles that are also sometimes called as synergies, or more precisely muscle synergies. Now, let us discuss the case when inertia and torque and angular acceleration interact, right. So, just like you have Newton's law, F is equal to m a, you also have m is equal to I alpha, where I is the moment of inertia, right. Now, this means to produce a particular acceleration, I have to produce torque that is influenced by moment of inertia, right. Now, in the case of so let us take the same case of flexion and an extension. So, there is a extensor flexor here, the torque produced by the flexor is flexor torque and the extensor torque, right. So, essentially the joint angular acceleration that we discussed in the, so that is that alpha is this, right, that is influenced or affected to a large extent by the moment of inertia of this, right. So, that is another thing that contributes to the situation. Once again same this changes depending on the joint configuration. So, as in the details will change depending on the joint configuration. One more thing before we move, before we finish the class, one more thing. We said that there are muscle synergies, coordination between multiple muscles that produce an action. Essentially what you see in healthy people who have learned to produce a movement, you see there is fine coordination in such a way that only the minimally required muscles are active minimally to produce a given movement. This is because they have learned this multiple times and they know what amount of force in which muscle at what point in time will produce success at the task. However, if you are a beginner in a given motor task, there is some task that is given and you have no clue or you have never done that before in your life, then it is not expected that the energy that is expended will be minimal, right. You will be producing more forces than required and there will be a larger amount of co-activation, right, than required. So, that means that will be energetically inefficient. So, essentially the amount of co-activation or the amount of energy that is expended in performing a task is a measure of skill that is there. So, if you are highly skilled, you will produce a smooth movement with minimal energy expenditure, whereas if you are a beginner, the same movement will require a larger amount of energy to be produced, because many more muscles than required will be activated to a higher level than required. This is something that you can see. You are trying to learn a task, say you want to learn punching on a keyboard, right. Initially you will be like pressing 1, 2, 3 discrete disconnected movements, right. Whereas you have practiced a lot and you want to use the same keyboard for producing the movement, right. You have practiced a lot. After that you will make movements that are smoother in such a way that are well timed and the muscle activations are appropriately timed and the activation levels are appropriately controlled to such an extent that the energy expense is lowered. This is a hallmark of skilled or well learnt movements. Okay. So, in this class we have discussed how joint range of motion affects muscle torque that is produced and how moment of inertia affects muscle torque that is produced. We have also discussed learning and skill level and other such things. So, with this we come to the end of this lecture. Thank you very much for your attention.